Okay, objective 9 asks you to relabel graphs and then say something about the resulting functions. Relabeling gets a little more complicated than what we're doing right now, but we're laying the foundation. So there are basically three things we can do to relabel graphs. One, we relabel the x-interval, and for now, the length of the x-interval is going to be the same. Okay, the length of the x-interval from -2 to 2 is 4. Length of the interval from 0 to 4 is 4. Okay. Now, y-interval, in this case, we relabel the y-interval, leaving the x-axis where it is, by leaving the left end, or the left end of the interval. The first number in the interval is going to be 0 both times, but the second number is going to be, in this case, 3 times the first number. We want to see what that does to the values of the function and so forth. Okay, the y-interval here is 0, 4, and we do change that interval, but we keep its length 4. We change the interval to 2, 6, it still has a length of 4. So the y-interval, the size of the units in the y-interval is not going to change here. The size of the units in the x-interval is not going to change here, but the size of the units on the y-interval here will change. Okay. Anyhow, let's go ahead and do this and see where we go with it. Okay, so the x-interval, -2 to 2 is going to become 0, 4, which means that -2 is going to become 0, 2 is going to become 4. Halfway between 2 and 4 is 2, so the halfway point will be here. And then halfway between 2 and 4 is 3, and halfway between here and here, of course, is where 1 used to be, so there's 3. And here's going to be 1. And then you could have 2.5, you could have 1.5, and so forth. So these are now going to be the values on the y-axis. My original graph was graphed with dotted lines for the axes, and that's a convention we want to start following. And my original labeling for the basic extended quadratic function, or squaring function, the numbers are in parentheses. Same with the y-axis. Okay, so here we have 0, 1, 2, 3, 4, now on the orange axis. And now the y-axis, of course, occurs when x equals 0. So the y-axis is going to have to move to here. So this is our new y-axis. And now here's our function sitting off to the right of the y-axis. So what we did was we added 2 every x value, and now the coordinates of every point are going to add 2 to the coordinates of every point we had on the original axis, as we've seen. The table for the new function, and normally we write the whole table. I'm not going to include the numbers that correspond to -1/2 and 1/2 just for brevity. But it would be a good idea to do that. Okay? The y values are going to be the same at 0, 1, 2, 3, 4 as they were at -2, -1, 0, 1, and 2 for the original function. That is, here the y value is clearly going to be 4. When x is 1, the y value is going to be 1. When x is 2, the y value is going to be 0. When x is 3, the y value is going to be 1. When x is 4, the y value is going to be 4. Okay? Now, what is this function? Okay? Well, when x is 0, it's a squaring function. What number would you square to get 0? Well, either -2 or 2. Okay, well, as it turns out, this table fits x minus 2 squared. Okay, y equals x minus 2 squared. 0 minus 2 is negative 2, gives you 4. 1 minus 2 is negative 1, square that gives you 1, and so forth. So what happened was, adding 2 to every x value gives you a new function that's y equals x minus 2 squared. Okay? Now, adding a number at every x value makes a function f of x into the function f of x minus a. Minus the number, okay? So let's say adding a number, and right now we'll call the number actually I'm going to call that number h because that's a standard number we use, standard letter we use. So okay, adding a number h to every x value makes f of x into f of x minus h. In this case, and let me just go ahead and do this. For example, f of x equals x squared becomes f of x minus h. And of course, if f of x is x squared, f of x minus h having replaced x, becomes x minus h squared. Okay? Replace x by x minus h. This is what we get. There's our new function. And if we evaluate that function, everything works out. So that's what happens when we add a number to every x value. It shifts everything to the left. Okay? Running out of room here. Shifts the y-axis to the left 2 units. Okay. In this case, what happens is actually fairly simple. We change this interval, y interval, from 0 to 4 to 0 to 12. Before I do that, I intended to do it over here. These values here remain 4, 2, and 1. So the y scale is the same as it was. Here the x scale is going to be the same as it was. It's still going to be negative 2, negative 1, negative 1/2, 0, 1/2, 1, 2. So now make that axis solid, and it corresponds to the numbers that aren't in parentheses. Okay, this axis changes. So this becomes 12, and of course this is 0 down here. Well, if we go from 0 to 12, halfway on the interval from 0 to 4, halfway would have been 2. Halfway to 12 is 6. And halfway from 0 to 6 would correspond to where 1 was, that's 3. And then if we want to label the 1/2, it would be 3/2. And then we would have 9 here, where 3 would have gone previously. And probably should put that in there. Okay, so if we do the table, what we've done is we've multiplied every y-coordinate by 3. Okay, 3 times 1 is 3, 3 times 2 is 6, and so forth. Made the interval 3 times, we just multiply every value by 3, and we see this happens, and this happens. If we make our table, I'm making an abbreviated table. You would want to include the x equals 1/2 point and the negative 1/2 point, but we can still see what happens using this, okay? Now we know, and of course we need to be familiar with these basic functions, we know that the y value here was 1/4, right? Now if we project over here, that's going to be 1/4 of 3, which is 3/4. Negative 1 is going to become 3. 0 is going to be undefined. The 1-2 point will be 3, and the 2-1 point will be 3/4. Okay, we compare to, and I'll just use white chalk here, the table we have for the original function. I really should include the 1/2, but I'll let you do that. The negative 1/2 and 1/2 x values. What's the comparison? Every one of these y values is 3 times corresponding y value over here. If you include the negative 1/2 and 1/2 points for the y values here are 12, y values over here would be 4, be the same. Okay, you'd be multiplying them all by 3. So we conclude that this is y equals 3x squared. 3 written carelessly again. Times 1 over x squared, and of course this is 1 over x squared. Because this is your basic reciprocal square graph. And I really didn't say that. So let's make sure this is clear. You should recognize this as the basic reciprocal square graph, having made it a number of times. In any case, the original graph was a basic reciprocal square graph, had this partial table, could have included the negative 1/2 and 1/2. Should have. You would. Okay, over here we have the coordinates after relabeling, and we see that the coordinates are are consistent with saying that y is 3 times 1 over x squared. So when we multiply all the y values by a number, well, that multiplies to 1 over x squared by that number. So we could say that multiplying y values by a number that I'll call A, changes the function f of x to the function a times f of x. Again, illustrated by this example, which I kind of garbled a little bit, but hopefully you got it. If you have a problem with that, we'll go over it again in class, because it's real important stuff. Okay, now, over here, we have the basic exponential function. Probably ought to tell you that from the beginning. The extended basic exponential function. And we're going to change the y interval from 0, 4 to the interval from 2 to 6. The x interval is not going to be affected, so we'll make that solid and write these numbers again. Again, without the parentheses. Over here, well, this is going to become, and what I just did was wrong. So, ignore what I've done here so far. I'm going to fix it and do it in a separate video, since we really haven't done that one in class.